Welcome back to ADE lectures, analog and digital electronics. Today we will see half subtractor and full subtractor in combinational circuits. So first we will see what do you mean by half subtractor. Half subtractor, also called as HS. What do you mean by half subtractor? So we know that 0 minus 0. How much? It is 0. 0 minus 1. How much? It is 1 with borrow. 1 with borrow. Similarly, 1 minus 0. It is 1. 1 minus 1. It is 0. So this is called half subtractor. 0 minus 0, 0, 0 minus 1. Actually, it is minus 1. That means 1 with borrow. Next, 1 minus 0 is 1. 1 minus 1 is equal to 0. This is called half subtractor. So now we will see the truth table. For example, this one is input. This one is output. So A and B, we will see outputs are difference and borrow. Difference and borrow. We will see how we will get. So this is A and B. So this is borrow and difference. So input and output. First we will see 0, 0. 0, 1, 1, 0, 1, 1. Okay. So 0 minus 0. What is the difference? 0 minus 0 is 0. So there is no borrow means we consider as 0. 0 minus 1 means 1. Difference is 1 with borrow. Borrow means 1. Next 1 minus 0, 1. And difference is there is no borrow means it is 0. 1 minus 1 is difference is 0 and there is no borrow means 0. So this is called half subtractor. This is called half subtractor. So bit by bit subtraction, 0 minus 0, 0, difference, 0 minus 1, 1 with borrow means 1, 1 minus 0 means 1, and 1 minus 1 means 0. So this is called half subtractor. Now we will find the difference. So this term we call it as M0, M1, M2 and M3. M0, M1, M2 and M3. Now we will find the expression for difference. This is also M0, M1, midterms M2 and M3. Okay, now we will find the difference equation. So difference equation means, so it is a 2 bits means 2 variables. So here A and B, that means we will use 2 variable K map. So 2 variable means we have 4 boxes. So this is A and this is B. So 0, 1, 0, 1. Previous, so M0 term 0, M1 term 1. So M0, M1 is 1. Next, M2 is 1. So this is M2. M3 is 0. Now we will map. So this is one map and this is other map. So for this map, we write it as A, B bar. For this map, we write it as A bar and B, because this row is 0 means A bar. So this column is 1 means B. So A B bar. So final equation is difference D is equal to A B bar plus A bar B. So this is the difference equation. Now we will see the borrow. So borrow means so this is A and this is B, 0, 1, 0, 1. So difference means M0 term, M1 term only, M1 term only 1. This is 1. Remaining are 0. That means M1 term. So M0, M1, only this one is 1. Remaining all 0. Oh, we have to map this one only. So what is the mapping results? So this row is 0 means A bar and this column is 1 means B, A bar B. So this is called borrow. So borrow is equal to A bar B. So this is the expression for difference and borrow. Now we will implement a logic, combinational logic circuits by using this expression. We will see now. So this A B bar plus A bar B is nothing but A XOR B. A XOR B. Yes, correct. This is A B bar plus A bar B is nothing but A XOR B. So we know that. So this is the XOR gate. This is the XOR gate. So this is A and this is B. XOR gate. This is A and this is B. What is the result? A XOR B. That is equal to, we call it as difference D. Difference or D. Okay. Next term is borrow means, so A bar B. So A bar B means we are adding one NOT gate and this one is B. This one is B. So this is called, so A NOT gate means here A bar and this is B. So final result is A bar B. That is equal to borrow. A bar B, that is equal to borrow or B. So this is called of subtractor. We are subtracting bit by bit of subtractor. Okay, now we will see the full subtractor. Uh, how to implement full subtractor. So understood this one, of subtractor. So I repeat now, please listen carefully. So of subtractor is nothing but bit by bit subtraction. So 0 minus 0, it is 0. 0 minus 1 means 1 with borrow. So minus means with borrow. 1 minus 0 means 1. 1 minus 1 means 0. Okay, this is called of subtractor. Okay, so for example here inputs are 0 0 0 1 1 0 1 1. So 0 minus 0 is equal to 0. 0 minus 1 is equal to 1 with borrow means 1. 1 minus 0 is equal to 1. Difference is 1. Borrow, there is no borrow means 0. 1 minus 1, difference is 0 and there is no bar means 0. So we are implementing expression by, it is a two variable map means we need two variable k map for implementing the difference equation and implementing the borrow equations. So finally we will get for borrow a bar b and difference a XOR B. Difference is A XOR B. By using this expression, we are implementing uh, combinational logic circuits by using basic logic gates. So this is called A XOR B difference and A bar B is borrow. So this is called off subtractor. Okay. Now we will see the full subtractor. So full subtractor FS. So full subtractor is nothing but we are giving three inputs. That means X, Y, and Z. We will get output borrow or difference. So this is called a difference. This is called difference. This is called borrow. This is called difference and this is called borrow. This is called full subtractor. What is the main difference of subtractor and full subtractor means? In off subtractor only we are using bit by bit only 2 bits, whereas in full subtractor we are using 3 bits or more than 3 bits. Okay, this is called full subtractor. Now I will write expressions. So X, Y, and Z. So these are the inputs. X, Y, Z. These are the inputs. So inputs means 3 means 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So these are the combinations. These are the input. These are the combinations. What are the outputs? What are the outputs? Difference and borrow. Difference and borrow. We will see now how we will get for 0, 0. So 0 minus 0, 0, 0 minus 0. So final difference is 0. Okay. Then borrow is there is no borrow means 0. Likewise, we are adding, see 0 minus 0, 0, 0 minus 1, 1. Difference is 1 with borrow means 1. Likewise, we are writing all the inputs 0, 1, 0, 0, 1 and 1, 1, 0, 0, 0, 1. Okay. So it is a 3 variable map means we need a 3 variable K map. So for finding the expressions for difference and borrow. Okay. For 3 variables we are finding difference and borrow. So for this we are reading this one is M0, M1, M2, M3, M4, M5, M6 and M7 like this. Have to find the expression for difference as well as borrow, and based on these expressions we are implementing the combinational logic circuits by using basic logic gates. So this is called full subtractor. Okay, this is called full subtractor. Next we will see the magnitude comparator. So in previous sessions, like first unit, we studied a comparator. So we are comparing two voltage levels. That is called comparator. So in digital electronics also, comparator logic is there. So how to compare two bits? We will see now. Okay. So this is called digital magnitude comparator. So a magnitude comparator is a combinational circuit. It is a magnitude comparator is a combinational circuit that compares two numbers A and B to determine whether it is A greater than B or A is equal to B or A less than B. It is called comparator. A comparator, a magnitude comparator is a combinational circuit that compares two numbers A and B to determine whether it is A greater than B or A is equal to B or A less than B. We call it as magnitude comparator. So here inputs are A and B. So this one is comparator. We are comparing whether it is A greater than B, A is equal to B, or A less than B. This is called magnitude comparator. Okay, first we will see the one bit comparator, how it will works. So this one bit comparator or digital comparator is both are same because we are using ones and zeros. That's why we call it as digital comparator. We seen in first unit, it is analog comparator. We are comparing two voltage analog voltages, that is called analog comparator. So now it is called as digital comparator. So here inputs are A and B. So first this one is B, this one is A. So 0 0 0 1 1 0 1 1. So these are the input. So how we'll compare? So first case is A greater than B. A is equal to B. A less than B. For example, here A is equal to 0 and B is equal to 0. That means A greater than B. It is false because both are zeros. That is equal. So false means 0. False means 0. Next, 0 is equal to 0. A is equal to B means 0 is equal to 0. It is true. True means it is 1. Okay. Then A less than B. So A is equal to 0, B is equal to 0 means this case is false means it is 0. Understood this one? I repeat, listen carefully. 0 minus or A greater than B. So A is equal to 0, B is equal to 0. This case is false. That means it is 0. So A is equal to 0, B is equal to 0 means A is equal to B case is true. That means 1. So this A less than B is equal to, it is false means it is 0. Then we will see second input, that is 0 1. So A greater than B. So A is equal to 1 and B is equal to 0. So A greater than B is true. True means 1. Then A is equal to B, it is false. False means 0. And A less than B. So A less than, already A is 1 and less than B means 0. It is false. False means 0. Similarly, 1 0 case. A greater than B. So A is 0. A is A is 0 greater than B. B means 1. It is false. That means it is 0. False means 0. Then A is equal to B. So 1 is equal to 0. It is not equal to 0 means it is false. Then A is less than, A less than, A, what is A? A is equal to, A is equal to 0 less than B. B means 1. So it is true. True means 1. So here also A is equal to 1 and B is equal to 1. A greater than B is 0. It is false. And A is equal to B. 1 is equal to 1 means it is true. Then 1 less than 1 means it is false. False means 0. So this is the comparator truth table, digital comparator truth table. Now we will implement the combinational logic circuits by using this. First, we will find the expression for A greater than B, A is equal to B, and A less than B. So how we will find the expression for A greater than B and A is equal to B and A less than B? So now you can observe it is a two variables. A and B are the two variables means we required 4 square, two variable K map. First we will find the A greater than B. So two variable K map means it is look like this. So this is B and this is A, 0 1 0 1. So here this is m0 term, this is m1 term. So one term is 1 means here A B bar. So this one is A B bar, A B bar. So this one is A B bar. A B bar. Okay. That is called A greater than B. That is called A greater than B. That is A B bar. Okay. We will get this one. Similarly, how we will get A less than B? This one. A less than B means, so this is square box. So this one is B, this one is A, 0, 1, 0, 1. Okay. Then min term, M0, M1, M2 term is 1, M2 term. So M0, M1, M2, this term is 1. So we map means this is A bar, vertical term, 0 means A bar, and horizontal line means B, A bar B. So this is called A bar B for A less than B. A less than B, A bar B. So likewise, we will get the expressions. So based on these expressions, we are implementing the combinational logic circuits by using the basic logic gates. Okay, this is A and this is B. We will get here C means A less than B and A is equal to B and A greater than B. This is called one bit comparator. This is called one bit comparator. So likewise, we will implement 2-bit comparators, 4-bit comparators, like that we will implement. So first thing is we have to write the truth table. Then based on the truth table, we have to write the expression for A greater than B, A greater than B, or A is equal to B and A less than B. After that, whenever we got the expression, then we have to implement the combinational logic circuits by using the basic building blocks like universal gates and basic gates. Okay, this is called one bit comparator. Now we'll see the 2-bit comparator. So for a 2-bit comparator, we have 4 inputs. 2-bit comparator, we have 4 inputs. That is A1, A0 and B1, B0 and 3 outputs equal. 3 outputs means this is equal. This is greater than. This one is less than. Greater than and less than. So for a 2-bit comparator, we have 4 inputs A1, A0, A1 and A0, B1 and B0 and 3 outputs. So output equal E is equal to 1 means if two numbers are equal, if Z is equal to 1 greater than means if A greater than B means then it is 1. If A less than B means L is 1. So this is the condition. Based on these conditions, we have to prepare the truth table. Then, according to truth table, we have to find the expression for E, G, and L equal, greater than, less than. So, based on the expressions, we can design the combinational logic circuits. So, it is similar to one-bit comparator. Okay. So, what is the next step? We have to write the truth table. So this is the truth table. So from this truth table, we have to find the equal. We have to find the equal. For equal, we will get this one, and greater than means we have to find the truth table like 4 variable map. We will get this one and less than. So by solving this one, we will get less expressions. So based on EGL, we will design the combinational circuit. So this is called EGL. So EGL. G and L. So this is called 2-bit comparator. So likewise, we have to design the 4-bit comparator also. Okay, this is 4-bit comparator. So this is called digital magnitude comparator. So let us briefly summarize what we discussed in this session. So in this session, we discussed about half subtractor and full subtractor. So half subtractor means bit by bit subtraction. So 0 minus 0, 0. So difference is 0 and bar there is nothing means 0. Then 0 minus 1 means difference is 1 and with borrow. Likewise, we are seen for 4 combinations, that is called off subtractor. By using the difference and borrow, we are implementing the by using K-map, we are implementing the expressions for difference and borrow. So based on the expressions, we are designing the combinational logic circuits by using the basic building blocks of logic gates. So that is called half subtractor. So full subtractor means we are add more than 2 bits. So full subtractor we will get also we will get a borrow as well as difference. So borrow is one expression and difference is one expression. Based on this expression, we are designing the combinational logic circuit, that is called full subtractor. Then we will see in the magnitude comparator, comparing of 2 bits, bit by bit, that is called comparator, equal, less than, or greater than. So these 3 conditions. This is called digital magnitude comparator. Okay. Okay, thank you.